For this lab, we ran tests in the wind tunnel with a circular cylinder in the test section. In this lab, we will analyze the pressure drag coefficient, the effects of the Reynolds number, the effects of surface roughness, qualitative and quantitative flow visualization, and sources of uncertainty and error in the experiment. For this lab, each team member was delegated a specific role to do during the lab. The first role was to set the wind tunnel to the proper RPM. The second role was to analyze the MATLAB data as it came in and attempt to plot the results. The third role was to stand on top of the wind tunnel and shine the floodlights or laser down into the test section from above. And the fourth role was to capture video of the flow. After the first set of results, we switched these tasks so that everybody got a chance to do at least two. Before collecting data for our lab, we went through the following startup procedure. First, we reviewed the safe working procedures for the wind tunnel. Next, we noted the ambient conditions in the lab and delegated roles. Next, we checked the cylinder dimensions and its position in the tunnel. Then we took a set of pressure data for the wind off condition, and last we ran a safety check and then started the wind tunnel.
To calculate the uncertainties, we used the LSR values for error bars because they are more meaningful than the standard deviation. The standard deviations for some of the pressure ports where the flow is more turbulent near the back of the cylinder were huge compared to other ports where the flow is more laminar, so it made the graph look wackadoo. We looked at the standard deviation for the Reynolds number from the data file and found that it was so small that it didn't show up well while plotting, so we left it out. We also had to leave out port 15 during our calculations because it was broken. And when we did calculations with the trip strip, we left out the ports that were covered by the tape.
When making our code, we decided to make pressure point at the center of each panel for calculating the pressure. The place this could make the biggest difference is at the stagnation point at the leading edge of the cylinder, where the surface is perpendicular to the flow. We made a large assumption that pressure point 12 was the stagnation pressure. This would mean in order to get symmetric graphs, pressure point 12 would have to be perfectly oriented perpendicular to the flow. And that assumption was incorrect. Upon looking at our data, it appears that pressure point 13 was actually the closest to the stagnation point, as the coefficient of pressure jumps up at that point, suggesting that's the stagnation point.
The Reynolds number that accompanies a set of data can be used to apply the information gained from that test to other situations with a similar Reynolds number, like larger scale models or different atmospheric conditions during another test. Even running the same test at the same speed at the beginning and end of an hour can result in a different Reynolds number between the tests, making it difficult to apply both of these data points to another situation. The pressure and temperature at the beginning of a test run can change the density and viscosity of a fluid, therefore changing the Reynolds number for that test run. To home in on the preferred Reynolds number for each test, the speed of the wind tunnel would need to be adjusted. Running all of the trials at the same Reynolds number rather than the same speed allows all of the data to be compared and used at a different scale together rather than needing to adjust for the change in Reynolds number between each trial.
At moderate to high Reynolds numbers, the drag is primarily the pressure drag. This phenomenon occurs because the range of Reynolds numbers, the boundary layer separates from the surface, and the pressure around the cylinder is no longer symmetric. The lack of symmetry causes a low pressure in the wake. Separation can be delayed by energizing the boundary layer. The boundary layer can be energized by generating turbulence in the flow to keep it attached to the surface. We attempted to generate turbulence in the cylinder flow by attaching trip strips to the surface. Changing the surface roughness of an object to improve its aerodynamic performance can best be seen in the game of golf. The ball has been designed with dimples all over the surface of the sphere, which helps keep the boundary layer attached and results in less drag on the ball. Our cylinder had trip strips attached on one location of the cylinder. This asymmetry likely yields less boundary layer reattachment. There is a limit with surface roughness where the object becomes so rough that the flow over the object becomes turbulent from the offset and the drag is increased.
Because the Reynolds number is a good metric to compare test results, we use it to analyze the coefficient of drag for the cylinder. We left out the ports that were covered by the tape and used our panel method to calculate the CD. We found that at higher Reynolds numbers, the CD decreased. This makes sense because the flow was more energized and stayed attached to the cylinder longer. Adding the trip strip energized the boundary layer even more, adding more turbulence and decreasing the CD by about 18 and 17% for low and high Reynolds numbers respectively. However, this may be a little deceiving because while the pressure drag was decreased, the friction drag was increased from the sandpaper and may have offset these results.
The equation for the potential flow around a cylinder comes from combining the stream function and velocity potential for a uniform flow in combination with the doublet over a cylinder. The equation gives us an expected value of coefficient of pressure based on the angular location along a cylinder.
The graph on the right from the lab manual shows the coefficient of pressure versus theta profiles for laminar and turbulent flow as well.
Here we have the actual values of coefficient of pressure compared to the ideal values of coefficient of pressure for each angular position. The stagnation point at the front of the cylinder occurs closest to port 13. The coefficient of pressure graphs should be symmetric around the stagnation point on a cylinder. A cylinder is symmetric, so the flow around the cylinder will be symmetric as well. But after analyzing the actual values for coefficient of pressure compared to the angular location, it was determined that the stagnation point of this cylinder likely occurs closest to port 13.
We compared our graphs to the lab manual profiles and saw that for both tests, the flow over the smooth cylinder was very laminar, as seen by the graphs on the left of both of the slides. Also, the trip strip did its job and added a lot of turbulence, which is shown in the right graphs.
The Strohel number is a non-dimensional number used to characterize the vortex shedding off of an object. The Strohel number describes the ratio between the inertia caused by the unsteadiness in the flow in comparison to the inertia of the unaffected flow. In other words, it compares the turbulence caused by the objects to the laminar flow that encounters that object.
This is a side-by-side comparison of the cylinder without the trip strip on the left and with the trip strip on the right. Both are tested at the same Reynolds number. While it looks like the vortex shedding frequency is quicker on the cylinder with the trip strip, it's actually slower. The video on the left was shot by a superior iPhone X at a higher frames per second, so it looks slower, but it's actually not. But if you look closely, you can see that the trip strip decreases the pressure drag exactly as intended, by delaying where the vortex begin and decreasing their size.
The Strohel number calculated for each of the test cases makes sense. The smooth cylinder has a higher Strohel number than the rough cylinder because it has a smaller boundary layer. This smaller boundary layer around the cylinder creates more turbulence off the back of the cylinder, increasing the Strohel number. The rough test strips added to the cylinder increases the thickness of the boundary layer around the cylinder, allowing the flow off the back to be less turbulent. Because the Strohel number characterizes the turbulence off of a body in comparison to the laminar flow before that body, it makes sense that the smooth cylinder has a higher Strohel number because it causes more turbulence.
Could there be 3D flow at the stagnation point at the center of the cylinder? I think the answer is yes, because at the stagnation point, the flow has no energy, and it'll move the first way it's jostled. So if there's any other force to that, it would be a 3D flow. It seems possible, but since there was very few particles at the stagnation point, it was very hard to visualize one way or the other. And also there are very few 3D visualizations of stagnation. How does humanity and nature adapt to prevent flow separation? For a palm tree, the answer seems to be the natural trip due to the roughness of the surface. As the air comes around, it creates a larger boundary layer, which takes a lot of energy out of the flow coming around the tree. The increased size of the boundary layer means that the air is going to be moving more slowly, and there's going to be a higher required wind speed for flow separation. As for the rocket in front of SpaceX, they're probably going to introduce a unnatural trip onto the surface of the body in order to obtain the same effects, because the surface appears to be very smooth otherwise. Would the cylinder experience lift force in the test section? A cylinder in real life would experience neither lift force nor down force unless it was spinning, which could create a difference in pressure. As long as the cylinder was centered in the test section height-wise, so that the boundary layer didn't affect it, and there's no asymmetries, meaning it was perfectly round, it shouldn't have experienced either a lift or downforce.
In this experiment, we determined that increasing the roughness of a surface decreases the Reynolds number and decreases the turbulence of flow around a cylinder. We were also able to determine the port location of the stagnation point of the flow around the cylinder from this experiment by observing the symmetry of the graph of coefficient of pressure. We were also able to observe the limitations of the ideal flow equations by looking at the difference between the ideal flow equation graphs and the actual flow we observed around the cylinder. Additionally, we experimented with different methods of visualizing the fluid flow around the cylinder. After using the smoke machine in combination with a laser and a floodlight, we determined that the floodlight was more effective based on the test setup that we had. We were also able to determine the unique sources of error and uncertainty with this particular fluid flow in our wind tunnel.